On our previous video, we were able to establish that this given equation is a non-exact differential equation. Hence, here, as we solve this, we will be using a separate set of processes, but we will also be using a portion of a process involving exact differential equation. Of course, this is in the form of m of xy dy plus n of xy, by the way, this is dx, I forgot, this is dx, and this is dy equal to 0. And we were able to establish that they are non-exact. This is non-exact because we're able to identify the partial derivatives of the two functions with respect to a specific variable. We might be showing the same here because we'll also be using the values. But let me use here a smaller width of my pen so that I could use some space. And we also have an example before where we use 2 pages, so I might be using the same here. So please bear with me. This might take 15 to 20 minutes of discussion because I really need to discuss this thoroughly. So first, let's start with identifying m of xy and n of xy. M of xy is paired with dx, so that's simply this one here. You have 6xy. And your n of xy is what is paired to dy. You will have 4y plus 9x squared. In the previous video, we're able to solve the partial derivative of m with respect to y. As we treat x together with 6 as constant, its first derivative is 6x. And our partial derivative of n with respect to x, as we treat y as a constant, hence the first derivative of 4y is simply 0, but the second term can be, since it only has x variable, this is actually 18x, giving us a result of 18x. We can see that they are not the same. That is why this is really a non-exact differential equation. Okay, what we need to do here now is, since we are to solve and they are actually considered to be, or this is not, the equation is a non-exact differential equation, we need to identify certain, what do you call this one? Integrating factor. So we have 2 different forms of integrating factor. We can have mu of x and mu of y. Whichever would be easier for us to solve. Whatever would that be, we are going to multiply that on the entire original equation to come up with a different form of equation that can be considered as an exact rather than non-exact. That is why I told you earlier, we might be using same steps for exact, but that would be on the middle part. Okay? The formula for mu of x is e to the power of the integral of f of x dx. And mu of y is e to the power of negative integral of f of y dy. Hence, we need to establish first f of x or f of y so that we could have this integrating factor. So the formula, let's start with f of x. If this is possible, then we'll be using mu of x as an integrating factor. Now, we would like to emphasize that f of x is possible once we could reach a function that will only contain a variable x, given this formula, 1 over n times the difference of the partial derivatives. That's why we still shared here the value, or the expressions for the partial derivatives, so that we could actually present here f of x or f of y if possible, or whichever is easier. So you have 1 over your n is this one here, 4y plus 9x squared. You will have 6x minus 18x. Okay, so you will have 1 over 4y plus 9x squared times negative 12x. But here is the problem. We cannot really remove here y, because if this is really intended for f of x, whatever would be the expression that will pop out, it should only contain variable of x. But this, no matter what we do here, will still have y. In short, there is a problem in solving f of x, and mu of x here as integrating factor is actually not possible. This is why we will skip to the second formula for f of y intended for mu of y. If this is possible, then we'll be using mu of y as our integrating factor. But if it's not, then probably we can no longer solve for this non-exact differential equation. The formula for mu of y uses 1 over m. That's the only difference here. Times the same difference, partial derivative of m with respect to y, minus, that's y, the partial derivative of n with respect to x. Okay? So we know that to be minus 12x, so we can really substitute it here automatically. Your m is 6xy. 1 over 6xy times minus 12x. And we can really see here that it's possible because this is under multiplication. Aside from this, separated by addition. With that, we can cancel x now. And of course, 12 divided by 6 is 2. You will have negative 2 over y. This is our f of y, and this only contains one variable, and that is actually y. Okay? So I'm showing you the two steps to differentiate them. With this, our integrating factor of mu of y is e to the power of, take note of this, negative integral of f of y dy. E to the power of negative, we have here negative 2 over y dy. So you could have here e to the power of positive 2 integral of 1 over y dy, which gives us e to the power of 2 natural logarithm of y, which could be transformed into e to the power of natural logarithm of y squared. With simplifying this, our integrating factor mu of y instead of mu of x is equal to simply y squared. Okay? So this is still on the first parts of our solution. Okay? So with this would be multiplied to our entire equation here. I actually identified a specific process here. I can copy this, by the way. Yeah, I will copy this. Hey, sorry. I cannot copy that one. So sorry. Let me do it again. Yeah, I can copy that one here. Copy, Abby, pasting the equation here. That's my bad. So that's 6xy dx. Let me rewrite it here. 6xy dx plus, you'll have 4y, the quantity of 4y plus 9x squared dy equal to 0. Again, this is a non-exact differential equation as already identified earlier. But once you multiply the integrating factor on both sides, you will have y squared times 6xy dx times the quantity 4y plus 9x squared dy. Of course, 0 times y squared is just 0. The assumption here is this should return into an equivalent equation that is actually exact. Let's continue. 6xy cubed dx plus, you have here 4y cubed plus 9x squared y squared dy equal to 0. Let's see if this is really a exact equation now. We will have another m to differentiate with our original m and n. Let's just simply call it m sub 1 of xy, which is 6xy cubed, this here. And our n sub 1 of xy, you will have 4y cubed plus 9x squared y squared. Let's see if this is really an exact equation now, this one here. So you will have the partial derivative of m sub 1 with respect to y. We'll be treating this as constant. So you get the derivative of y cubed, that's 3 times 6x, so that's 18xy squared. Okay, 18xy squared. Continue for our partial derivative of n sub 1. Again, we're using the sub 1s over the, or with respect to x. So this is constant, that's 0, plus this would be, sorry, not the x, because this could be written as 9y squared, that's constant, x squared. So derive x squared with this as constant, so that's 2 times 9, 18, y squared x, or you can rearrange this to 18xy squared now. As you can see, they are equal to each other, and this is now an exact differential equation. So from a non-exact, we came up with an exact differential equation. In this part of the video, we will be using the processes of solving exact differential equation. I don't have much spaces here, but let me try to use another page later. To solve for an exact differential equation, focusing on this, not the original, because the original is a non-exact and this is what is exact using the integrating factor we did earlier, we will have to show f of xy equal to c. But f of xy is equal to this form, m sub 1 xy dx plus g of y. Okay? So your m sub 1, going back to our m sub 1, here is m sub 1. So 6xy cubed. Integral of 6xy cubed dx plus g of y. Since we are taking the integral of dx, so 6 and y cubed, we can move that out. 6y cubed integral of x dx plus g of y. Moving that here, pardon for this. So let me just copy it first. Integral of x dx plus g of y. You will have 6y cubed, and the integral of this is x squared over 2 plus g of y. Not writing any c yet. Okay, this would be divided. You will have 3 x squared y cubed plus g of y. This is our f of x y, to which I'll be copying because I'll be moving on a separate page. So please bear with me. I already mentioned this will take a lot of time. So moving on another page. So you'll have to paste here, just like this one. This was our equation, our f of x that was formed earlier by the given processes. The point here is we will be solving for this. Okay? We'll be solving for that so that it would be really a function or expression with y alone. So we'll have here the partial derivative of f with respect to y. This is actually the partial derivative of this. You will have 3x squared y cubed plus g of y with respect to y. So we are going to take the derivative of this function with respect to y, treating this as a constant. Okay, so the first order derivative of that is given as, this is actually 3x squared times 3y squared, the derivative, times the first derivative of g of y, leaving with the result equal to 9x squared y squared plus g prime of y. Okay, since we would like g of y, not g prime of y, we are going to look into this relationship. The partial derivative of f with respect to y is just equal to your n sub 1. Okay, n sub 1, not the original n, but n sub 1. Going back here, this is not the item we're talking about because that's non-exact. This is what we're using here. This is what we will be using, this one here. So let me copy this as well, n sub 1. Okay, copy, move to the other side. Let me paste it here. Okay, so our n of xy is this. So if we're going to equate them using, sorry for that, using this, you have 9x squared y squared plus g prime of y is equal to n sub 1, which is this, 4y cubed plus 9x squared y squared. We have the same entries here. You can cancel that. In short, g prime of y is 4y cubed. And since we would like g of y, take the integral dy, and the other side as well, 4y cubed dy. This will return to g of y, the item we would like to solve to complete our solution. This other side, you can take out 4y cubed dy. That's actually 4 times y to the power of 4 over 4 plus c. Just in the meantime, let's just not add c there. So this will be removed. So g of y is simply equal to y to the power of 4. Okay? So with this, okay, last two steps, copy, copy. Last two steps. Okay, so we will have now our final form of our solution, f of xy being equal to 3 x squared y cubed, this here, plus g of y, which is y to the power of 4. The last step here is, since we would like to have a solution equal to c, simply equate this to c. So you have 3 x squared y cubed plus y to the power of 4 equal to a certain c, and this is our solution now. So this ends the process of solving this non-exact differential equation following this very lengthy solutions. But this is very important to really answer the given item. So return to the item here. So from a non-exact differential equation identified earlier by the previous video as well, we came up with a certain f of x or f of y that will help us solve integrating factor, which could transform the non-exact differential equation into an equivalent, I mentioned, equivalent exact differential equation. And from that, we'll be duplicating the processes involved in solving exact differential equation. Thank you very much for watching.